Okay, so now let's talk about classification of differential equations. So before we talk about classification, I'd like to talk about what a differential equation actually is. So a differential equation is defined by an equation where we have an unknown function, or a function we're talking about. It doesn't necessarily need to be unknown. Let's call this function y of x, and let's set this function equals x squared. And a differential equation is where we make use of this y of x function and its respective derivatives inside this function. So we could have something like y double prime plus 2y prime plus y of x, or just y, because most of the times when we're writing differential equations and we write y, we actually mean a y of x, and when we mean a y of x, we mean x squared. So equals to, let's say, sine of x. So this will be a differential equation because we are making use of this y prime, the double prime of this function, 2y prime, y of x, and we have sine of x. So these, since we are making use of the derivatives of this function y, we are able to call this a differential equation. And when we want to solve a differential equation, our main goal is to find what y is, and I just gave an example that y is x squared, but our goal is to find solutions for this differential equation where we would be able to plug this function in here and it will generate this result on the right hand side. So this is what we can call a differential equation. Now let's talk about how we can classify differential equations by order. So the first thing we want to do when we're classifying is to find which order this differential equation is. So over here, let's start with an example. We have a differential equation y double prime minus 2xy equals to x squared sine y. We know that the highest derivative of this equation is 2, the second derivative. We are taking the second derivative, y prime y. So this would mean this differential equation's order is 2. So basically when we want to find order, we are looking for the highest derivative in this differential equation. So over here we have 4y to the fifth. This actually stands for derivative when we write it in parentheses. This is a derivative symbol. So the fifth derivative of y minus 8y equals to 0. So since the highest derivative is 5, the differential equation's order will be 5. And this is called the Leibniz notation. If you say you have taken calculus 2 or 1 or 3, you should be familiar with this notation. This stands for dy dx stands for y prime, and these exponents on d and x are giving us the which derivative we're talking about for this function y. So we have the sixth derivative of y over here plus cosine of y times y prime equals to 5. So we have the sixth derivative, which means the highest order in this differential equation will be 6. Now I want to talk about linear form in differential equations. So now this is another type of classification. When we are classifying differential equations, there is a linear or nonlinear classification. So the basic definition of a linearity in a differential equation is given by this formula up here. I know this formula might be looking confusing, but it's actually relying on very simple steps. So first of all, we are having a p sub n x function, this function, times a certain derivative of y, and these are different p of n minus 1. These are just different or same x functions. And over here at the end we have a y of x. So what linearity means in a nutshell is that we will have y double prime or y or higher y to the n, let's say yn derivative, these could be existing in the function by themselves, not inside a function. And then you can multiply them with any kind of x. Any x function is fine. Okay, and we could set this equal to a q of x function, x squared, or a q of x function could be a constant or a zero. And I know a lot of people will ask, well, how is 5 equal to q of x? Is this true? Well, 5 times x to the 0 is a way of explaining this function in a function of x. So yes, 5 is a function of x, or a function of y, or whatever you want to talk about. So when you talk about a function of x, you are just saying this function is made out of x and x terms only, or constant terms. Well, if you have, let's say, xy, you would say that this is a function of x and y, so we would have q of x and y equal to xy. So these kinds of functions where we have y alone, when I mean alone, basically y cannot be in, like, let's say, e to the y, or cosine of y, or I don't know, 1 over y, all of these, or ln of y, these are not good ways to classify linear differential equations, and these would cause non-linearity in a differential equation. So if you have terms like cosine of y, 1 over y, ln of y, e to the y, these examples could be extended, but as long as we have y inside a different function as an input of that function, these would ultimately cause this differential equation to lose its linearity. Now, before we move on to some examples, I'd like to talk about homogeneity in differential equations. So, homogeneity means that the right-hand side will be 0 in a differential equation. So, we could have a differential equation looking like y double prime plus 2y prime plus, let's say, 2 equals to 0. As long as the right-hand side is equal to 0 and the left-hand side is made out of y or y prime functions, we are able to call this differential equation a homogeneous differential equation. So are they cases that the right hand side is not 0 and we have a homogeneous differential equation? And the answer to that question will be yes. There are cases that the right hand side will not be 0, but there will be homogeneity. For example, let's say y double prime plus 2y prime plus, let's say, y equals to, let's say, 5y. Okay? Is this a homogeneous differential equation? Well, many people would assume that this right-hand side is not equal to 0, so this must be a non-homogeneous differential equation. Well, unfortunately, that's not the case here. In this case, you are able to manipulate this equation and move this equation to the right and make this equation look like y double prime plus 2y prime minus 4y equals to 0. And since all of these factors are applicable for the standard form, since we have functions of x here, and this is a function of y prime, or y double prime, or other y derivatives, this shows that this works. So what we can say about homogeneity is, anytime on the right hand side we have a factor of y, or y prime, or y double prime itself, and multiplied with a function of x, of course, when I talk about a function of x, I'm assuming we're talking about a function of y of x. Sometimes some classes use y of t as an example, where the input will be t. Well, in this case, we're using a x input. So in these cases, when we're multiplying the right hand side with a y or a y prime or those derivatives, we are able to move this to the left hand side to make this equation look like a homogeneous differential equation. Now let me give an example of a non-homogeneous differential equation. Y double prime, I'm gonna go with the same differential equation on the left hand side. Let's say this will be, let's just say x squared. So let's try it. Let's see, the right hand side is not 0. Is there anything we can do about homogeneity? If we move this to the left hand side, well, there will be an x term, but it's not multiplied with y or y prime or y double prime. Let me just illustrate that real quick. We would have something like this. However, there's no y here. This is not a good thing because you need to have, if this was multiplied with a y or a y prime, we could make this work, but unfortunately this is not the case, so this will be non-homogeneous. So now let's move on to some examples. The first example is y triple prime minus 5x squared y equals to x tangent y. Well, the order for this differential equation will be 3 because the highest derivative is 3. So now let's move on to this differential equation for order. 9y double prime minus 4y prime plus 5 equals to 0. Well, ultimately the highest derivative is 2 on y, so this will be a second order differential equation. And on this one we have a Leibniz notation, d4, which is the fourth derivative of y, plus e to the x y prime equals to 0. So the highest order for this differential equation will be 4 because of this term. Now let's think about linearity. For the first equation, the first thing that catches my eye is this tangent of y term. And as I said before, we do not want this. We do not use y as an input for another function. So this will cause it to be nonlinear. In this second problem, there is nothing that is causing a nonlinearity. We have a y double prime, y prime. We don't have a y, which is fine. So this will be a linear differential equation. Over here, likewise, there is nothing crazy going on here. We have a fourth derivative and a derivative, but these are just multiplied with a x function, so these are just fine. So this is a linear differential equation. So if we don't have linearity, we don't need to even bother with homogeneity because it will not be homogeneous anyways. So we can now think about homogeneity for these problems. Well, unfortunately, these functions are homogeneous because the right hand side is 0, so I picked quite easy examples here. Over here, there's nothing that's causing it to be a non-homogeneous differential equation, so we will say this is a homogeneous. Likewise, over here, this is a non-homogeneous differential equation. Let me ask you one question about homogeneity over here. I want to use the same derivative, same function I had up before, and let's set this equal to x squared plus x minus 1. Well, is this, well, the order is going to be the same, the linearity is going to be the same, but the homogeneity will be minus for this one because these terms are causing it to be non-homogeneous. Even if we try to move this to the left hand side, it would ultimately fail because we were not multiplying this with a y function. Therefore, this is a non-homogeneous differential equation.